journals, and currently he's the editor-in-chief of the electronic journal Mobility. His interests include concentration inequality, functional inequality, concentration inequalities, functional inequality, and diffusion operators. He's written over 100 papers, which have been cited an amazing 2,600 times, over 2,600 times. So without further ado.
Well, thanks for the introductions, and thanks also to the panel committee for the invitation. It's of course a great honor to take part in this Congress, and thanks to our host for the organization. So the purpose of this talk is to present some illustrations of heat flow methods to geometric and functional inequalities. Of course, heat flow and semigroup interpolation are very classical tools in mathematics, going back to the so-called Duhamel formula from the 19th century and maybe before, and then has been used a lot in PDE, probability theory, dynamics, and so on. And over the last decades, semigroup interpolations have become relevant in geometric and functional analysis, in particular in the study of various Euclidean and Riemannian geometric, functional, and transportation cost inequalities, with a wide range of applications and illustrations. To mention a few: heat kernel bounds spectral analysis, multiple integral inequalities and isoparametry, measure concentration, statistical mechanics, optimal transport, and the study of metric measure spaces, and so on. It should be pointed out that within this framework, the geometric aspects are developed mainly through the notion of gradient bounds, which are related to convexity and Ricci curvature lower bounds, as in particular emphasized in the seminal paper by Bakri and Emery from '85 on hypercontractive diffusions. So the selected topics that we would like to present today will concern various forms of these inequalities, these geometric and functional inequalities, logarithmic Sobolev inequality and the Li-Yau parabolic inequality, a topic on isoparametric inequalities, then optimal transport and Harnack inequalities, and if time permits, a few words on Braskamp-Leaf inequalities and noise stability. However, before addressing these topics, let us start with a simple basic model example in order to illustrate the principle, the heat flow interpolation principle, and the way it interacts with geometric bounds. And this model example is, so I'm sorry, I forgot to mention that several of the results presented here are joint with Dominique Bakri, and presented in particular in a recent monograph with him and Yvan Gentil. And so before addressing some of these topics, let us start with a basic model example, namely the so-called logarithmic Sobolev inequality. So what is the logarithmic Sobolev inequality? In its very classical form, it's going back to the work of Gross in the 70s, and it expresses that for the standard Gaussian probability measure on Rn, for any smooth probability density with respect to the Gaussian measure, the integral of f log f, that is the so-called entropy or relative entropy of the density f with respect to gamma, is bounded from above by 1/2 of the integral of the Euclidean length square, grad f square, divided by f, d gamma, that is the Fisher information. So if you change f into f square into this inequality, it looks more like a classical Sobolev inequality, namely if you take a function whose gradient is in L2, then the function itself is not in LP or any p strictly bigger than 2, the exponent degenerates, but you still keep a logarithmic factor, and the function is in the ordered space L2 log L. On the other hand, one important aspect of this inequality is that no constant depending on the dimension appear. It's completely dimension-free, and in particular, it opens the possibility to consider analysis and Sobolev embeddings in infinite dimension. And the logarithmic Sobolev inequality has proved useful in a number of areas. So infinite dimensional linear analysis, as mentioned, has been useful in its equivalent hypercontractive form, and it has been used to study convergence to equilibrium of various kinetic equations and Markov chains. It has been used in measure concentration. It appears in information theory and optimal transport, and it was also used by Perelman in its study of the Ricci flow towards the Poincaré conjecture. There are numerous different proofs of the logarithmic Sobolev inequality, at least 15 different ones. But perhaps the simplest one is perhaps this heat flow interpolation proof. And let us briefly present this proof, starting from the very basic heat semigroup on Rn, given by the Gaussian kernel here, or written in its integral form with respect to the standard Gaussian measure. And this heat semigroup, of course, solves the heat equation, the associated heat equation, with the Laplace operator, with initial condition, the function f. So to use this heat semigroup in a proof of the logarithmic Sobolev inequality, the idea is actually to consider a so-called heat kernel inequality and to study for any smooth positive function f, and for any t strictly positive, the quantity, the entropy along pt, or pt of f log f minus ptf log ptf, at any point, simply omitted here. And to see the connection with the standard form of the logarithmic Sobolev inequality, you simply observe that by the integral representation, if you take t to be a half, any other value of t, of course, would do the same by scaling. And if you take, for example, x to be 0, any other point would do the same by translation. You see that the distribution of pt is exactly the standard Gaussian. So that if you consider this relative entropy along the semigroup, you exactly get the relative entropy under the normalization that f is a probability density with respect to the standard norm. Now, the starting point in a heat flow proof of the logarithmic Sobolev inequality is simply to consider this entropy along the semigroup and to interpolate it. And this is one basic instance of this so-called Duhamel formula. Namely, you simply write that this expression is the integral of its derivative, using in particular that P0 is the identity. So you get this representation. You use the heat equation and a little bit of calculus, namely the chain rule both in time and space, to obtain that this derivative is given by a kind of Fisher information along the semigroup. So as a result, you get this integral representation of the entropy along the semigroup, which is the basic interpolation step. Now the next step is very easy too, is simply to observe that on this basic example of the Euclidean heat semigroup, you have a commutation between the relative action of the gradient and the semigroup that we will interpret later on as a curvature condition, in this case a null curvature, a flat curvature. And using this commutation property and taking the Euclidean length in this inequality, you get, by a simple use of the Cauchy-Schwarz inequality along the Markov kernel PU, you get this upper bound, and you then you see that if you take u to be t minus s, you see that the ratio which is inside this integral here, this term and this term, is bounded above by this expression. So if you choose u to be t minus s, that's the upper bound that you get. And using the semi-group property, ps composed with pt minus s, that's pt. This doesn't depend on s anymore. And you are left with sufficient information along pt. And when t is a half, for example, you exactly get the logarithmic Sobolev inequality in its initial formulation. So you see that this proof only relies on two basic tools, this interpolation procedure, plus the Cauchy-Schwarz inequality, which is the only place where there is an inequality in this proof, and in particular, it allows you to get the equality case in the logarithmic Sobolev inequality. Now let us take a slightly different look at this proof. So we start from the heat flow interpolation. Let us denote by phi this Fisher information along the semi-group. And what we basically showed is that using this gradient commutation, we basically showed that this function phi is increasing, so that phi of s is less than or equal to phi of t, and you get the inequality. Now, of course, in order to prove that the function is increasing, we learned a long time ago another way to do, namely to take derivatives. So why not try to differentiate this function phi? So before differentiating this function phi, let us observe that by the chain rule, there is a very simple rewriting of this Fisher information along the semi-group, which is this expression, simply by taking grad of the log and writing what it is. And the point is that if you take the derivative of phi, what you get is a very similar expression, almost the same, simply that you replace the grad square by something else, which is this gamma 2. And gamma 2 is a second order operator, which is by now called the Bakry-Emery operator, and it is this expression, which of course on Rn is simply the Hilbert-Schmidt norm of the Hessian of your function, of your smooth function f. But for geometers, of course, they will immediately recognize that this gamma 2 is one half of the very classical Bochner formula in Riemannian geometry that involves the Ricci tensor of your Riemannian manifold. And on the basis of this identity, it's pretty obvious that if you are dealing, for example, on Rn or on a manifold with non-negative Ricci curvature, the two terms defining gamma 2 are non-negative, so that the function phi you are considering its derivative is positive, and you get that it's increasing, and you get exactly the same heat kernel inequality along now the heat semi-group associated with the Laplace-Beltrami operator on the manifold. So exactly the same proof is working in this more general context based on the gamma 2 analysis. And this gamma 2 analysis has proved extremely useful to establish a number of heat kernel inequalities and functional inequalities, Sobolev, logarithmic Sobolev, Poincaré, Nash, and so on, using the underlying geometric information which is contained into the gamma 2 object. You may also consider not only non-negative lower bounds on the curvature, but any lower bound would do more or less the same. And to actually connect with the first proof that we showed of the logarithmic Sobolev inequality which was using this commutation property between the gradient and the semigroup, you may actually show that this curvature condition is precisely equivalent to such a commutation property, from which you may also prove the logarithmic Sobolev. So that's for the basic spirit, this basic example, on which we see how the heat flow interpolation arguments develop and how they are connected with the underlying geometry of the space on which you are looking for heat kernel inequalities. Now let's do one step further in this proof. First of all, by observing that exactly the same argument produce inequalities in the other direction, namely lower bound on the relative entropy, with a kind of a similar type of Fisher information, but slightly different. And this reverse form of the logarithmic Sobolev inequality is extremely useful into the study of gradient bounds, and we will come back to it later on. So let us start again with this heat flow interpolation. This is a summary of the argument. You develop the entropy along the semigroup by the integral of its derivative, which is this phi, which is this Fisher information along the semigroup, and then you take the derivative of this function phi, and you see the gamma 2 operator, which is entering into the picture. And then if you can show that the gamma 2 is non-negative, you can prove that phi is increasing, and so on and so. But actually, if we look at the argument that we developed, we actually wasted a term. We used that, for example, on a non-negative Ricci curvature manifold, the Ricci term is non-negative, and then we say that this is a square that's also non-negative, and then we got the inequality. But we wasted this term. And in a sense, this is connected with the dimension-free aspect of the logarithmic Sobolev inequality, which doesn't depend on the dimension. However, you might want to still keep some information on the dimension. So we still keep the Hessian and use a simple trace inequality to bound from below the gamma 2 by something depending on the dimension. So times delta, the Laplace-Beltrami operator of h squared. So that the derivative of phi is bounded by below, not by 0, but by something that depends on the dimension. And then you need to integrate. Of course, that's a little bit more difficult than only integrating phi prime bigger than 0, but still you can do it. What you get is not that nice, it's a bit heavy. It's a kind of dimensional form of the logarithmic Sobolev inequality. It's a bit heavy, but it's still, it's clear that it's an improvement of the logarithmic Sobolev inequality, either by the simple inequality log of 1 plus x is less than or equal to x, or better when n goes to infinity, because this is precisely the dimension-free feature of the logarithmic Sobolev inequality. So we will not be interested into this inequality, which is interesting by itself. We will actually be interested into the reverse form, because as before, there is a completely analogously reverse inequality where you get a lower bound on the relative entropy along the semigroup, which is as ugly as the other one. But there is something implicit in this expression, and explicit from the proof, is that what is inside the log should be positive. What is inside the log should be positive. And here you actually recognize a very famous inequality, which is the Liao parabolic inequality. Just use the chain rule formula to develop delta of the log, and what you get is this. For any smooth function, positive smooth function on a manifold with non-negative Ricci curvature, and n is t strictly positive, you have this inequality, which is this very famous Liao parabolic inequality, which was proved at the origin using the maximum principle, and which is embedded here in this heat flow argument using the logarithmic Sobolev inequality. So for the further purposes, let me just recall that this famously Yau parabolic inequality has been used a lot towards heat kernel bounds and Harnack type inequalities of the following type. So what was developed so far, starting from Rn and then to manifolds, can be developed similarly in the setting of weighted Riemannian manifolds. So you have some smooth weight here on the Riemannian measure, and the associated second order operator is the Laplace operator, and then there is a drift due to the weight on the measure. And in this context, exactly the same argument go through, and you may define a so-called non-negative curvature dimension condition. But now the gamma 2 has to take into account both the curvature of the manifold in terms of the Ricci curvature and also the convexity properties of the potential that you put in the weight. And similarly, you may consider curvature dimension for any lower bound on the curvature in this form. And you can actually even go further, so-called notion of Markov triple, in which you are dealing with a semigroup with generator L and underlying invariant measure, mu. And then you have the carré du champ, so-called carré du champ operator, which measures how far your diffusion operator is from the derivation. For example, on a smooth manifold for the Laplace operator or the Laplace operator with drift, this gamma would be simply grad f grad g, as is classical. And then you have the gamma 2 that you have to construct in this abstract context, and the gamma 2 is constructed with a formula which is completely identical to the definition of the gamma, replacing products in the gamma definition by the gamma. And then you have a curvature dimension which is completely similar, bounding from below the gamma 2 by something depending on gamma and something depending on the dimension through LH squared. So far for the first topic that we wanted to present, and let us turn to the second one, namely isoparametric type inequalities. So of course it's very classical that for the classical isoparametric inequality for the Lebesgue measure expresses that with fixed volume the balls are the one with the minimal surface measure. Now the question is, what is the isoparametric inequality when you have another measure on Rn, and for example the Gaussian measure? And the answer is that the extremal sets are the half spaces, which may be thought as balls with centers at infinity. And the isoparametric inequality states that and if you take a Borell set with the same measure then as a half space, then the surface measure, the Gaussian surface measure of your set is bigger than the corresponding one for the half space. And one way to define this Gaussian surface measure is through the notion of Minkowski content. A sub epsilon here is the epsilon neighborhood of your set. An equivalent way to present this isoparametric inequality is via the Gaussian isoparametric profile. So you consider the infimum of all the surface measures when you fix the measure of your set. And by the isoparametric inequality, since half spaces are the extremal sets, you may compute the Gaussian isoparametric profile on half spaces. And since half spaces are basically one-dimensional, the Gaussian isoparametric profile is something which is given by a one-dimensional function, which is constructed from capital phi, which is the distribution function of a standard normal, phi being its derivative. And this composition then defines the isoparametric profile. And if you rewrite the isoparametric inequality, it's an inequality between the Gaussian surface measure and the Gaussian measure of the set itself via this isoparametric profile. Gamma plus of A is bigger than I of the Gaussian measure. So typically, isoparametric inequalities are proved using symmetrization arguments or rearrangement arguments. But actually, there are also heat flow proofs of such geometric inequalities. And here is one result in this context, in the context of weighted Riemannian manifold or weighted one or even Markov triple under the non-negative curvature condition, but it would be similar for any lower bound on the curvature. And there are heat flow proofs of such isoparametric inequalities by means of inequalities of this type. So this is again a heat kernel inequality, which involves this isoparametric profile I. By the way, this is stronger than the logarithmic Sobolev inequality by a simple approximation of f. And why is this inequality useful, and why this inequality has some isoparametric content? Simply because if you, for example, look at the basic instance of the Euclidean space, as we did before in case of the logarithmic Sobolev inequality, assume that you are on Rn, take t to be a half. So Pt is the distribution of Pt is the standard Gaussian. And what you get is this inequality, where again I is the Gaussian isoparametric profile. And now in this inequality, you simply plug an indicator function. And due to the fact that the isoparametric profile at 0 at 1 is 0, this quantity is 0. On the left, you get I of the Gaussian measure. And on the right, you are left with the L1 norm of the gradient of f, which approximates the Gaussian surface measure of A, and you get the Gaussian isoparametric inequality. So this recovers the classical Gaussian inequality, but actually tells you much more in terms of a comparison of the isoparametric profile comparison with the Gaussian one. And this works for any lower bound on the curvature. But there is a challenging open question here, which is the fact that we are not able to take any form of dimension in this inequality. And one challenging question would be actually to provide a heat flow proof of the standard isoparametric inequality on the sphere, for which extremal sets are geodesic caps, and more generally to reach the Levy-Gromov theorem, comparing the isoparametric profile of, for example, a compact manifold with the same dimension and curvature as the standard sphere. As for logarithmic Sobolev inequalities, there is a reverse form, which is this inequality, which expresses a not so easy to explain property, but actually very useful, which is that each time you take a function with values in 0 or 1, if you compose it, if you take and this is shape. You can do the same under any lower bound on the curvature, and it actually contains a whole family of Parnac type inequalities. Here is another application, another Parnac inequality which is covered by this reverse form of isoparametry. This is a kind of infinite dimensional version of the Lie Parnac inequality. Again, there is no dimension in this inequality because it's infinite dimensional. Actually, note that there is a difference with the Lie Parnac inequality, that the squares here is outside and inside on the right. It makes a rather big difference with the classical inequalities.
And actually there is a whole family of inequalities replacing 2 by other powers. And there is a variant which is the log-Harnack inequality. So pt of log is something like log of pt, and you compensate by the distance between x and y at which you are looking those two measures. And actually this further Harnack inequality opens the links to optimal transport inequalities, and in particular to an already famous inequality, which is the HWI inequality due to Otto and Villani. So this inequality is a kind of strengthening of the logarithmic Sobolev inequality via a new term here. So here is the relative entropy, here is the Fisher information, and in between you have the so-called Wasserstein or Kantorowicz-Wasserstein distance between the two measures, namely the initial measure nu, which is the Riemannian or weighted Riemannian measure on your manifold, and the measure nu with density f. And this inequality has been quite useful and important in the study of Ricci curvature lower bounds on metric measure spaces by Lord Villani-Sturm, and in the study of various related transportation cost inequalities. It was proved at the beginning using PDE methods, and is actually a very simple consequence of the preceding log-Harnack inequality which we emphasized, and the connection is made very easy by the very classical Kantorowicz-Rubinstein duality that expresses the Wasserstein distance in terms of the Hopf-Flachs infimum semigroup. And using this duality, using the Hopf-Flachs semigroup, what you have actually to do is simply to recast the log-Harnack inequality in terms of the Hopf-Flachs semigroup, and what you see is this inequality, from which it's very easy to see that you can bound from above the relative entropy along Pt by the Wasserstein distance for the large values of T, and then for the small values you use, as usual, the Fisher information, and optimizing in T, combining the two, you get the HWI, H for entropy, W for Wasserstein distance, and I for Fisher information. And just for the record, let me mention that there is actually a full duality here expressed again in non-negative curvature. There is a full commutation property between heat and Hopf-Flachs semigroups that is at the root of the heat flow contraction in Wasserstein distance, which has been studied by several authors during the last year. But actually completed 2 items at the same time, covering the applications to optimal transportation by the Harnack inequalities, which appeared as a reverse form of Isoparametric. And now in the very last part, let me briefly consider Braskamp-Philippe inequalities and noise stability. To start with, let us just briefly recall some objects that were explicitly or implicitly considered so far. So gamma is a standard Gaussian measure, and T rho or PT, through this relation here, the Ornstein-Uhlenbeck semigroup, which is the semigroup with generator, the Ornstein-Uhlenbeck operator associated with the quadratic potential of the standard Gaussian measure. And for this Ornstein-Uhlenbeck semigroup, you have this integral representation, which is very similar to the one that we had for the standard heat semigroup on R. So the noise stability relation with heat flow that I would like to emphasize in this last part is a recent result by Michel and Niemann, which states the following. So you fix a rho, so fix a time, if you like, in terms of the Ornstein-Uhlenbeck semigroup or the Hermite semigroup. Look at a function j with 2 variables, and look at 2 smooth functions f and g. Then the theorem by Michel and Niemann is the following. If you look at this double integral, So this double integral is an integral with respect to two standard normal in Rn with a correlation rho, or correlation rho times the identity. So here you have the correlation, x and y are two independent standard normal on Rn. And this expression here is exactly the same as the one that we had in the definition, in the integral representation of the Einstein-Uhlenbeck algorithm. So the theorem is that, of course, this is not true for all function j, as you can guess. But the theorem is that this double integral is bounded from above by j of the integrals, if and only if the following concavity property on j holds true, namely that it's a kind of distorted concavity property. You take the Hessian of your function j, and then you put a rho on the anti-diagonal, and you ask for this matrix to be non-negative definite. Call this property j to be rho concave. Okay. So the proof is a simple but nice application of heat flow methods. You simply replace f and g by PTF. So you let run time along f and g, take derivative, and you see that what is inside here is precisely the rho concavity property, this Hessian with a twisty rho, which is negative. So once you have such an inequality, of course, one has to look at examples of function j for which this is of some interest. Here's one first example. We take a power type function on R plus cross R plus. Power type u to the alpha, v to the beta for alpha and beta in between 0 and 1. And it's a very simple exercise to check that this function is rho concave, if and only if you have this relation between rho, kind of noise that you put in this inequality, and alpha and beta, the exponent in the definition of J. So if you write the concluding inequality, what you get is the following. And now what you may do is you may change f into f to the 1 over alpha and j into j to the 1 over beta in order to use a duality argument in f, and at the end you get that T rho, or PT if you prefer, in terms of Einstein-Uhlenbeck sum group, in LQ norm is bounded from above by the LP norm of G with this relation between rho and Q and P, and this is the famous Nelson's hypercontractility property, which is, by the way, is equivalent to the logarithmic Sobolev inequality. So there are various multidimensional extensions of this result. Let me just go very briefly over the next 3 slides. This is a multidimensional version of what we just saw, with a function j which is arbitrary but of m coordinates, and then you get a condition which is the analog of the rho concavity. A typical illustration is the so-called geometric Braskamp-Leap inequality, which is going back to Keith's ball, stating that under a suitable decomposition of identity for the same j function as before, a power type j function, you have a kind of improvement of the standard Hölder inequality in the directions given by the vectors AK. And of course, all this stuff, all these Braskamp-Leap inequalities are related to the more general family of Braskamp-Leap inequalities and the study of their maximizers given by Gaussian kernels, which have been studied extensively by heat flow methods by Carden-Liblos and Bennett-Carberry-Tristan. But the point here is actually not to focus on this family of this example, this first example of J function, but on another one. This is the main point of the contribution by Mosel and Niemann. And here is another function J, which is of interest. So in this definition, x1 and y1 are independent standard normal in dimension 1. So with distribution capital phi, and then you look at phi phi inverse here and here. And this is again the same convolution that we had in the definition. And it's an exercise, not so difficult but a bit tedious, to show that this function is indeed rho concave. Okay? So it is rho concave, so you get this inequality. So this is exactly the result between rho concavity and this integral inequality. Now, in this inequality, just plug two indicator functions. So in particular, the right-hand side is pretty easy because it's exactly J of the Gaussian measure of A and the Gaussian measure of B. And if you go back to the very definition of the function J, which is given in terms of this distribution function of the Gaussian measure in dimension 1, what you get is the following, namely that the probability, which is on the left-hand side, that if you have a couple of standard normal in Rn with correlation rho, or rho times the identity, the probability that this couple belongs to A cross B for two Borell sets A and B is bounded from above by the same quantity where A and B have been replaced by H and K, where H and K are parallel half spaces with the same measure as the initial sets A and B. So this is known as Borell theorem. It was proved again as the isoparametric inequality using rearrangement methods, and Michel and Niemann actually proved that it's embedded into this heat flow procedure. It is known as Borell's noise stability theorem because you may define this notion of noise stability if X is in A, and then if you take a small noise, not necessarily small, but if you take a perturbation, a noise perturbation by adding Y, you still are in A. And what Borell theorem is saying is that half spaces are the most stable. And this has been used using via invariance principle in the study of majority stables by Michel, O'Donnell, and Ledoux. So let me just briefly conclude with two observations. First of all, it's possible to bridge this discussion about noise stability with the one on isoparametry that we had before. Namely, if you start from this Borell noise stability theorem, you may actually get isoparametry simply by not so difficult heat flow description of the perimeter of a set A. And of course, provided you may compare the noise stability here, you can also compare the Gaussian surface measure so that you recover the Gaussian isoparametric inequality from the noise stability theorem. And the last slide is just to mention some extensions. This doesn't only work for Gaussian measures, it works for families of log concave measures in pretty abstract setting. The study of the deficit in both the isoparametric and noise stability theorem has been studied recently by Eldan, using actually further tool from heat flow interpolation, but more in terms of stochastic calculus. And finally, let me mention several developments in Boolean analysis, and in particular a new proof by Michel Niemann of the majority stable theorem, precisely using this function J that was used in this heat flow. And it's time to conclude and to thank you for your attention.
Are there any questions? All right, well, it was a beautiful talk, and let's